Okay, hey everybody, we're live. So the Div 3 round just wrapped up. So yeah, just going over the round as a whole, I think the difficulties were pretty good. Definitely a smooth curve toward the beginning, definitely like several easier problems, which is good. Just giving more people more chances to do problems, and maybe the later end of the problem set was a bit on the easier side this time, but I think that's totally fine. There's not that much need to like go super hard toward the end. And yeah, so it looks like the biggest drops were from C to D was a decent drop, and then actually it was pretty smooth still even after that. Enrique Kai says, Neil, where are you? It's bright there. Yeah, I have like a light in front of me to help make it brighter. Otherwise, like it would be super dark and you wouldn't be able to see me. Yeah, so I saw a lot of people in chat said they got 3 problems, which makes sense given this difficulty curve. It definitely seems like it jumps up at D. Yeah, and then in terms of standings, yeah, pretty smooth sailing for me. I didn't have any wrong submits, which is good. Looks like people are already trying to hack me, so that's funny. And I did kind of a funny thing where I went for E before D, because since E has 2 subtasks, you can get like a better penalty by doing E earlier, but I'm not sure it paid off because I took a while to do E relative to the other problems. Yeah, I think it was on the easier side, but I don't think that it was like a problem. I think that's fine. Okay, so I do see several people asking to start from D. I oh wow, we did get a hydrate, by the way, at the beginning. So it was from System Flaws. Okay, and now we have an IRL word ban, which this will be pretty hard. So the word I'm not supposed to say for the next 5 minutes is I. So we'll see if I get. Okay, so I'll just say we all the time. Okay, so we'll see if we can do that. So basically we'll start from A through C and go through them quickly, since a lot of people want to talk about D. So here's problem A. So you have a sequence of integers, and the sequence is from 1 through n, and you've got to write A1 on the left side, A2 on the right side, and then A3 right next to A1, A4 right next to A2, and so on, all the way into the middle. And you're given the finished sequence, and you want to construct the original sequence. So, for example, if you're given this sequence, you want to reconstruct this, where this was constructed by doing, 3 here, 1 here, 4 here, 1 here, 5, 9, and then 2, and so on. And we have a hydrate. Oh man, this IRL word band is going to be hard. Maybe I should have. Oh, I already messed up. Maybe we should have made this more expensive. Okay, so for this problem, it's super simple. You just simulate it. In my code, just have this simple loop. For the even indices, you take the front of the B array, and then I erase it here. And then for odd indices, you take the back, and then I erase it here. Oh, I keep saying I. This is really difficult. Okay, so for this in particular, this is n squared runtime because erasing the begin is not super fast. Here it's fine because n is only up to 300, so not super big. So let me just make sure. Yeah. If you want it to be faster, what you can do is you can make b into a dec, and then you get the pop front method, which is O of 1. And so you can pop the front and pop the back in O of 1. And now this is linear time. But quadratic time is totally fine here. And so this is good enough to pass. So we'll just talk about B and C quickly as well. So for problem B, you have a string S, and you want to do this one operation where you can take some substring of the string, so characters from I through J, and you remove that substring. So you have a new string which is just 1 through I minus 1 and J plus 1 through N. And so some examples of what you can do, if you have this string, you can remove this and you can get 2020. You could also remove, maybe I'll make this a little bit bigger. You can remove this and get 2020. It's saying you can remove this and get 020, or you can remove this 0 and you can get, 2019 220. So a lot of different options here, and you want to find a way to build the string 2020. And you're allowed to perform 0 operations. Okay, so for this problem, one thing that's convenient is you're given n is at least 4. Otherwise, we would have to check some special cases. Or really, we would just check if n is less than 4, then it's always no. Yeah, and so we need to output yes if we can make 2020 and no if we can't. So the main thing we want to notice is basically we're going to remove a substring from the middle, and we want to make sure that what remains is 2020. So what that means is we'll essentially end up with some prefix of the string and some suffix of the string. So for example, in this case, we're removing substring. We'll end up with some prefix, so here 20, and some suffix, so here also 20. Or another example, we can remove this. We have a prefix of 2 and a suffix of 020, and we want those to add together to make 2020. So that's basically what we do to solve this problem. We just loop through all of the lengths of the first part from 0 to 4, which means the second part at the end is 4 minus that. And we just check, is s dot substring from 0 to first plus the substring of the last second characters. If that equals 2020, then we're good. And so that way we just print yes if we found anything. And the reason that the n less than 4 case is tricky is because actually now if we have just a case where the string is 20, well, first of all, we'd be out of range. Actually, I don't know if we can avoid the out of range. Yeah, we'll just get out of range. But one thing that would be tricky is we would have a prefix of 20 and a suffix of 20. And so we would think we can make 2020, but we can't. Luckily, the problem gives you n at least 4, and so you don't have to worry about that. But just something to watch out for on different problems to make sure you don't go out of bounds. Okay, we'll quickly go through problem C. So for problem C, you're given a positive integer x. You want to find the smallest positive integer number. I don't know why they said integer number, actually. You could just say integer. That has the sum of digits equal to x, and also all of the digits have to be distinct. And x is between 1 and 50. So here, the way we should approach this is just try to make some observations. So first of all, we would never want to use the digit 0 in the number because we could just remove it and get a smaller number. And it never helps with getting the sum, right? And so we can think about a few cases. So let's think about x equals 24 as an example. So there are a lot of ways we can make a sum of 24. Let's see, one example could be something like, let's see, maybe 2, 3, 4, 5, or 2, 3, 4, 6, 9, something like that. This would be 15. Yeah, that would be 24. We could also go, 4, 5, 6, 9. A lot of different options. And let me make this bigger. Okay. And the first observation we make is that out of all the options, we definitely want the shortest number of digits, like the shortest string possible, the shortest or the smallest number of digits. So anything with 4 digits is better than anything with 5 digits. And once we do that, we can see here for 24, for example, we can get 4 digits, but we can't get 3 digits because 3 digits, the highest sum we could get is 987, which is, oh, sorry, did I mess this up? Sorry, I meant to do 25. So let's just bump these up. Okay. So yeah, if we want a sum of 25, yeah, this is one way to do it. This is another way to do it. Yeah, okay. And then we can't get 3 digits. It's no good because this only adds up to 24. And this is the biggest sum we can get since we have to have distinct characters or distinct digits. And so now that we know the answer is going to be 4 digits, we can think about, okay, what 4 digits do we put? Well, first of all, we should definitely sort the digits, right? 4579 is less than, 9754. And then the other thing we can notice is if we can drop an earlier digit and increase a later digit, that would be better. So for example, instead of 4579, we should go, 3589, right? Which is better. So I guess we could say, this is less than this. And then we can just keep repeating this process. 2689 would be better. And then 1789 would be better. And then now we have basically the ideal number here because it's a 4-digit number. It starts with a 1. And then these are already totally maxed out in order to get that 1, right? And it turns out the general solution to this is that we just use 9, 8, 7, 6, and so on to get as close to the sum as we can. And then finally, we get the smallest first digit that we can. Because basically our number will be it will start with something and then it will end with, some string that's looks like 6, 7, 8, 9, right? The biggest digits in order. And the reason for that is if we don't end with something like 6, 7, 8, 9, we'll have something like 3, 5, 7, 8, 9, and we'll have a digit here that could be bumped up, namely the 5, which could bump down our first digit, right? Or in the case of 1, 5, 7, 8, 9, we could bump up this 5 to a 6, and we could actually, so I'll just write this out. Sorry, 2, 6, 7, 8, 9 is better. We could actually bump the 5 up to a 6 and just remove a digit. And so that's why the string has to end with this kind of sequence 6, 7, 8, 9, 5, 6, 7, 8, 9, like that. So the code itself basically looks like this. So first of all, if we're bigger than 45, we can't do it because the biggest thing we can get is 1, 2, 3, 4, 5, 6, 7, 8, 9. And that adds up to 45. And then otherwise, we're just going to use 9, 8, 7, 6 all the way down until finally the number we have remaining is actually less than the current number. And the code, you can look through the code, it just kind of builds this string from right to left. That's why I'm always adding to the beginning of the string. And so on. And then finally, we add the remainder. And so maybe just to illustrate how this code kind of works, we can just show a couple different cases. So for example, for 1, 2, it'll just return the number itself, 9, and then 10. 10 will do 19, 11 will do 29, and so on. And then maybe just for some more examples, 30 gives 6, 7, 8, 9, 31 gives 1, 6, 7, 8, 9, and then 2, 6, 7, 8, 9, and so on. And then once you get to 36, you add another 1, 37, and so on. And then like the final behavior before you get to 45 looks kind of like this. And then you get negative 1s. And so that's the idea. Oh, we have a hydrate. Actually, I haven't been checking. I might have, if I missed a hydrate, let me know. Also, I think, I assumed we ran out of the IRL word ban a while ago, but I realized I lost track there. Oh, thank you so much, Mount ACR, for the subscription, for the sub. Yeah, it was a little hard to do the IRL word ban in the middle of trying to explain these solutions, like thinking through what is the best way to explain the thought process. If I fail the IRL word ban, you should get refunded. I think that's a little too strict, but I do admit I did fail it multiple times. So I'll consider maybe doing like a half refund later. We'll see. Someone asked, where did I go to college? Yeah, I went to Harvard, did CS. Okay, so we had a lot of people asking about starting from D. So, well, we're there now, or we're there now, and let's just get to it. So, Cyanide wants a full refund, but you've been redeeming hydrates, and I've been doing all of those. So, here, I'll just do an extra one for you. Someone asked about my compiler. I assume what you mean is my script here that I'm running. It's just I have like a couple different like compile scripts, and it just adds like different flags, kind of checks the code and so on. And then there's like a run script which just calls the compile and then runs the command. Just like a couple minor things. It's not super important. It just helps me like, you know, be like 1 minute faster, which can matter for different contests. Oh, the LSP setup. Yeah, maybe I can show that in a later stream. Yeah, it's like, I don't know. It's like mildly helpful, I would say. It's not like super important. It's more critical to just like solve problems and so on. Okay, so let's go into D. So problem D, we have an array A. We've got n integers. And what we can do is we can pick an index I and then add AI to either of the neighbors. So we can add AI to a minus 1 or add AI to AI plus 1. And obviously we can only do that if it exists. And then after we do that, we remove the ith element from the array. And then A gets 1 shorter in length. So we're kind of squishing the array down. And we can do that no more than n times. Technically, we can do that no more than n minus 1 times. Right, the two things above are one single operation. So here's an example. If you have 31662, you can take the 1 and then add it to the 3, you'll get 4662. You can take the 4 and add it to the 6, you'll get 1062. You can take the 2 and add it to the 6, you'll get 108. And then you can take the 8 and add it to the 10, you'll get 18. And you can stop at any point. You want to know what's the minimum number of operations you need to do to make everything in A equal. So the array can be any length, but all the elements have to be the same. And then n is up to 3000, and then the array elements are up to 10 to the 5th. And yeah, we have this multi-test case set up, but the sum of n doesn't exceed 3000. So if we did like n squared, we would be fine. And first thing to note is it's obviously always possible because we can always get the array down to one element. And if it's just one element, then we're good. So we don't have to worry about any, that's why there's no -1 case here. And the way that I would approach this is I would think more about this operation. Like what does it mean? What does it really do? And another hydrate. And what we can realize is the operation actually contains a lot of like duplicates. So if we took the 4 and added to the 6, it's actually the same as taking the 6 and adding to the 4, right? Either way, we'll get 10, 6, 2. So really what the operation is it's just like you pick 2 consecutive elements and then you replace them with their sum. And that's all of it is. And this kind of I, and then choose I minus 1 or I plus 1 only if it exists, and then remove I. It's just like extra details because really it's just pick any 2 consecutive things and then replace both of them with the sum. So if we think about doing a bunch of these operations, then we'll end up with an array where essentially every element in the new array is just like a subarray of the old array. So to just give a quick example, let's just put some random numbers, right? And then we can do some operations. So maybe we'll take both of the 2s, and then we'll do the 4 and the 6. And then we'll do 7 and 8. So we'll end up with this array, but really all we did was, maybe I'll just get rid of the commas actually. Okay, we'll end up with this array, but really all we did was, not that, here. Oh yeah, that's right, okay. All we did was just kind of cut the array into a bunch of pieces and then replace each piece with the sum, right? And that's how we get this. 15 here, 3 here. Yeah. So that's all the operations really do. And then once we know that, then we can just figure out a lot easier whether we can get to an array with all elements equal. So in particular, we can just iterate the length of the final array. And if we know that length, then we know what the element that everything needs to be is, because the element that everything, or the value that everything will need to be is sum divided by length, right? Because the sum of the whole array stays the same, but the elements are all equal, which means they all have to be sum divided by length. And so to code this, it's pretty simple. Yeah, so it's pretty simple. We just iterate. So here I'm just iterating count, which is the count of the, or just the number of elements in the final array, which is the same as what I wrote here with length. So first of all, sum mod count has to be 0 or else we already fail. And so otherwise this is our goal. And then basically we just go left to right in the array. We just add things up and we try to get to goal exactly. And if we fail to do that, then we just set our fail boolean to true. And once we're at the end, if we manage to do that successfully, then the answer is n minus count. The reason is if you have an array of length here, 7, and you end up with an array of length 4, that means you did 3 operations in between, because each operation reduces the length by 1. So yeah, so I coded it this way. I have like a 2-pointer sweep with I and j. You don't have to do this. I think you can just loop from left to right and just add things up. Whenever you hit exactly goal, you can just count that in and then basically just throw out the, or reset the sum to 0. And just make sure that you always found the goal and you never went above the goal or like got stuck below the goal at the end. Okay, a lot of people are asking for your explain. Please don't spam all caps though. So yeah, so this is just an example. This is not to end up with equals. This is just to show what is the operation doing. And the operation is just taking, like cutting the array up into a bunch of subarrays, taking the sum of each subarray, and then putting that together. So what we're doing is in this loop we're iterating the count of the number of elements at the end. So here would be 4, right? And if there are 4 elements in the end, so maybe I'll pick a real example to try to demonstrate this. Okay, I don't really like any of these examples too much. So I'll just make up something. Okay, so something like that. And then the sum of this array is 40. Okay, and so if we're thinking about, what array can we end up with where everything is equal? Well, let's iterate the length of that final array, and we need to figure out if we can cut up the array into a bunch of segments that all sum up to the thing we're looking for. So if we want a final length of, just an example here, 4, then what we would do is goal is going to be sum divided len, which is 10. And so then we're going to go through the array here, and we're going to, basically cut it every time we get to 10. So this is 10, 4 plus 6. This is 10, and then 1 plus 2 plus 3 is 6, and then 4 more is 10. So we're good. And then 9 plus 1 is 10. And so we're good, and we did the whole array. And so this would give us a potential answer of n minus 4, right? And then to give another example where it actually doesn't work, we could say len equals 5. Then goal is going to be sum divided by len, which is 8. And so now if we try to cut up the array, we'll have 4. That's not enough. And then we'll add 6. And so we're actually at 10 already, which is bigger than 8. And so we know it's not possible. So the main idea is just think about what is the operation really doing? And then you're like, aha, okay, it's just taking the sum of a bunch of, it's just breaking up the array into a bunch of different subarrays and then taking the sum of each. And now we're thinking, okay, if we want a certain length of the final array, well, the sum of the final array is equal to the sum of the original array. So we know that if everything is equal in the final array, then every number is going to be sum divided by length. So if we want a length of 4 of the final array, everything is going to be 10 as a subarray. And so we just go through our array and look for sums of 10, and then we just cut it there. And then we have another 10, and we just cut it there, and so on. And so this is how we can build the final array that's just 10, 10, 10, 10. Right? And so if we pick a different length, we have a goal of 8, then we can find it's not possible here. And well, how do we know what length to do? Well, we just try all of them. And so this is what this outer loop is doing. Just try all the lengths. Okay, awesome. Looks like it makes sense to people. NumArt is asking about hacking. In general, for hacking, I think first you just need to really deeply understand the problem, and then you can try looking at code and see if there are different mistakes. Hacking is tricky because they've already passed the pretest, so they've already passed a lot of tests, and you're kind of looking for something that's missing, and so you're looking for corner cases often and things like that. The other thing you can do, I think, since in div 3 you can actually just get people's code. I guess I'll just Yeah, you could actually just like take their code and run it, and that could be a way to hack. You can't do that in a, you know, a round where hacking actually can bring you up in the standings, but here you can. Okay, so looks like we're good on D. We'll go to E. And E, so I thought E2 was the hardest problem here. For some reason, it seems like people don't agree with me. A lot of people got E2 versus F. Maybe about 2x, not like a huge difference. But yeah, I definitely thought E2 was harder than F. So anyway, I will, I'll try to go over like both of these at the same time since they're pretty similar. It's just that E2 is harder in constraints. And okay, so basically you've got a sequence of integers. Sequence A, it has length n, and the integers are from 1 to n, but you can have duplicates, so it's not necessarily a permutation. You want to find tuples of m elements where the max number in the tuple minus the min number in the tuple is at most k, and so the difference is no more than k. And this is kind of a more formal definition. So for example, if n is 4, m equals 3, k equals 2, then you can pick the triples 1, 2, 3, or you can pick 2, 4, 3, right? Whereas if you pick something like 1, 2, and 4, the difference is going to be 3, which is bigger than k, which is 2. And so this answer is going to be 2. They give you another example where a is all ones, so in that case it's actually just 4, choose 2, which is 6. In this version of the problem, you print the value mod 10 to the 9th plus 7. And E1, basically the only thing that's different in E1 is you're guaranteed k equals 2 and m equals 3. And you don't need to do modulo because the answer just fits into a 64-bit int. Okay. Oh, we got to hydrate. Taurus2412 says, should I watch this? I didn't even read E1. Yeah, so that's why I go over the problem descriptions as I'm going. So hopefully the problem makes sense to you now, and you can, if you want to, you can just follow along. And yeah, so just to make sure it's clear, just to go over the examples again, they have these. The answer for the first one is 2. Oh, sorry, I should go back to here. The answer for this is 2. Again, we can pick 1, 2, and 3, which has a max difference of 3 minus 1, which is 2. And we can also pick 2, 4, and 3, which has a max minus min difference of 4 minus 2, which is 2. And then, 1, 2, 4 is no good because 4 minus 1 is too big. Same thing with 1 and 4, 3, because 4 minus 1 is too big. So there are 2 options here. Okay, so yeah, so the first thing I noticed for this problem is that the order of A doesn't matter. Because we're just picking any m things, and we just care about the max of those m things and the min of those m things. It doesn't matter what order they come in. So, one way we could interpret that is we could just sort A. And so max is just the last thing and min is just the first thing. But a better way to interpret it actually is that we can just convert A into essentially like a frequency table. And so 1, 2, 4, 3 is really just a table that's like, okay, there's 1 of 1, there's 1 of 2, there's 1 of 3, there's 1 of 4, right? And then the same way, this 1, 1, 1, 1 array is just a frequency table saying, okay, there's 4 of 1. And now the less than or equal to k condition is a lot easier to think about. It's just like, we can only pick numbers between, x and x plus k. And well, how many numbers are between x and x plus k? It's just the sum of the frequencies in that range. Yeah, Alvisa Naya said, I tried sorting and going with pointers, but the repeated numbers muck that up. Yeah, exactly. So the repeated numbers get a little tricky there, and so it's easier to convert it to a frequency array. And so now that we have this idea for a frequency array, we can think about, okay, well, how are we gonna make sure the difference is at most k? And basically, we just do what I was saying, where between x and x plus k, there are some range sum of the frequency table numbers, and we can choose any m out of them. And so an initial idea for a solution could be something like, yeah, let's take the frequency table, let's take the, well, we take the prefix sums just to get a range sum quickly. And then if our first element, if the smallest element is a, and we want the biggest element of a plus k, then we can just add up frequency a through frequency a plus k, and then do a choose of m. The problem that occurs here is let's make an example frequency table. So here we'll have a, and here we'll have frequency a. So maybe we'll have like 1, 2, 3, 4. Frequencies could be like, 4, 6, 5, 9, something like that. And then we're saying, yeah, we can just say m equals 3, k equals 2. And so what we'll do here, for example, is, well, since k equals 2, one option is we could have numbers between 1 and 3. And so if like the smallest equals 1, right, then frequency 1 plus frequency 2 plus frequency 3 is going to be 15. And so we add 15 choose 3 to the answer, because out of these 1s, 2s, and 3s, we can pick any 3 of them and we'll be good. And then similarly, if smallest equals 2, then this is going to be 20. So we can add 20 choose 3 to our answer, because if we choose any 3 of these 20 between 2, 3, and 4, we'll be good. And then if you think about that carefully, the problem there is that we actually ended up double counting certain cases. So for example, if we actually use, a 1, a 2, and a 3, then we're good. We only counted it here and we didn't count it here. Or if we use, a 1, a 3, and a 3, same thing, we counted it here, but we didn't count it here. But the problem is, let's say we used a 2, and a 3, right? Then we actually counted that in both of these cases, because we counted frequency 2 and 3 here, and we counted them again here. So we need to, this is kind of like an inclusion exclusion. We need to subtract out those cases where we double counted them. And so here we would just be looking at, okay, frequency 2 plus frequency 3 is going to be 11, and so we need to subtract out, 11 choose 3, because these are the ones we double counted. And actually, if we do this, then we're all good. We can think about even, for example, let's say we just use only 2s. Then what happens is we counted that option once here. We counted that option again here a second time, and then we subtracted it out here. And so this is basically an inclusion exclusion idea. If this topic that I'm saying is new to you, you can read up on it here. The main idea is, if we want to, for example, count the number of things that are in the union of two sets. So let's say we have a bunch of sets. For example, maybe you have like n items on your desk, and like some of the items are rectangular, and then some of the items are black, right? And then A could be the set of items that are rectangular, and B could be the set of items that are black. And so if you want to count like the number of items that are either rectangular or black, you would count it this way. the number of rectangular items, plus the number of black items, minus the intersection, because those are the ones you double counted. And so you can get a lot more general. There's a whole bunch of different math in here, but that's the main idea. It's a good topic to just read up on a bit if you want to solve some harder Codeforces problems involving counting. But anyway, here it ends up being pretty simple. We just need to add up the ranges that have a difference of k and then subtract out the ranges that have a difference of k minus 1. So this is my implementation for E2. Just read the input, read an A, and then you create the frequency array, frequency A++ for every element. And then the key thing is I call a solve function, which solves k, and then I subtract out solve for k minus 1. And in the solve function, I just do prefix sums, and then I just count the number of things in a certain range of length. The length is actually k plus 1 because you're allowed to pick x and you're allowed to pick x plus k. Well, here I call the variable a. So you're allowed to pick a and you're allowed to pick a plus k. And so you just count the number of things there and add up that choose function. What is modint? So modint is this class that I use that basically helps you do operations mod, for example, 10 to the 9th plus 7. And it basically defines all of the operators for you. So you have plus, minus, times, divides, and so on. And then I also have this set up to calculate factorials and choose functions. And basically what that means is when I write the code, I can just do things like mod int total equals 0, and then I can just add something. And so I don't have to worry about overflow for one, and I don't have to worry about instead of doing this every time, I can just do like a much more natural plus equals and then return. And then another thing that's convenient is and then also I have minus defined, so I can just do very natural integer operations. And then another thing that's convenient is I have basically the cout operator defined as well, and so I can just cout a modint just fine. Did I make this? Yeah, I made this myself. Although I'm not the first person who has come up with this. Definitely not. I think I probably first saw it from maybe Eknerwaller or Ksun48, and then ended up just writing my own version. And yeah, so it does make your submission a lot longer, but it makes it a lot easier to write for yourself, and it makes it a lot less error prone. And I think that as long as you have good abstractions and encapsulation, it shouldn't make your code harder to read, because if I'm reading someone's code and I see this kind of modint thing, I'll just basically assume what it does and then skip over it, because it's all very natural definitions. You also have things like pow, for example, to take something to a certain power, which comes up a lot in counting problems and so on. Oh yeah, Crow, operator overloading is, yeah, it's a C++ thing. I think you cannot do it in Java. Well, we have a doppelganger in chat, Neil Wu H. Yeah, in Java you can do methods, but it doesn't look as clean. It's total equals total dot add, something like that. And so it definitely feels less natural if you can't overload the operators. This is something that I think Anand Oza mentioned in one of his streams as well, as a small reason out of the list of reasons why he switched from Java to C++. But yeah, key thing here is to think about counting the frequencies that are in ranges of the right length, and then realize we double counted, or actually more than double counted. We over counted certain things. And sometimes with inclusion, or usually with inclusion exclusion, you need to when you're counting things of length k, you add the things of length k, and then you subtract the things of length k minus 1, and then you add back the things of length k plus or k minus 2, subtract k minus 3, and so on. And it's just alternating sign thing all the way down. But on this problem, because it's only subarrays and it's not subsets, it actually ends up being a lot more convenient. So we just add the things for k and we subtract the things for k minus 1. And then we're good. It actually counts everything accurately. And so that's just something that if you're unsure about, I would just suggest like making your own kind of like frequency table, just playing with some examples. Try the counts for, pick a k, take the sums for k, and then subtract out k minus 1, and then think about like which ranges you counted, like double counted, and then you can realize that like we're basically perfectly subtracting out the double counted or the over counted stuff by going through k minus 1. Oh, I watched coding said you coded all of E2 and then you forgot to submit. Oh, that's really sad. Yeah. And then QUE asked how many contests does it take to get a rating? So it only takes one contest to get a rating. It's just that for div 3s, they don't actually give you the full standings right away. You have to wait for the hacking phase to finish. And then after that, you know, eventually ratings will update. So I think you can expect it by like, you know, something like tomorrow. And then I'll just add a couple comments. So we had a couple questions about choose. For choose, you can do a couple things to, basically you can just pre-calculate factorials and then inverse factorials. And then choose is just n factorial divided by r factorial divided by n minus r factorial. And so that's how I set it up. So this is O of 1 time. Yeah, you can look at like, kind of like any top competitor submissions to some of these counting problems, and they'll probably have something like this. And then what I'll say is for E1, for me, I just did the same thing that I did for E2 basically, except I remove the modent. I just do count choose 3 manually. But the main reason E1 is easier is because you don't have to figure out this kind of clever add k, subtract k minus 1 situation. You can kind of just like force your way through it, because it's you'll add like, we're just considering things of 3 elements that are no more than 2 apart. So like we'll add something like this, we'll add something like this, we'll also add something like this. And then we'll add this. And this will be like looped over all A. If we add all of these things up, then we'll end up counting the number of subsequences of length 3 that work. And so that's why E1 is a bit easier than E2. For E2, you have to think more about the inclusion exclusion. Dinesh BS, please stop spamming. You asked the same question something like 6 times. I've been doing programming for a long time, probably something like maybe like 15 plus years now. Yash Twitch Live asked, Neil, any idea why Eknerwala uses too many asserts in his code most of the time? So the reason for putting asserts in your code, and so for example, I have asserts here for like inverse choose, is that there are certain things that like you're depending heavily on a certain assumption for your code to work. And so asserts are a good way both for you to like check your logic, and so when you run on the samples, you know that certain conditions were satisfied, and then also to even just for readability, to make it clear in your code that these are the assumptions you're making. And so, for example, when I put an assert in this inverse choose function, I'm making this assert, which means I'm making the assumption that R is between 0 and n. And so if someone who wasn't me was using this code and they were just reading it, they would know that, this is something that is an assumption that they need to satisfy when using this function. Oreo redeem hydrate. Can asserts slow down your code too much? So asserts are pretty fast. It's not like a super big issue. I mean, if you do, one thing that can happen is like, if you do something like this, and you do like, I don't know, like assert, it's at least 0. Well, it's not the assert that's slow, but you did call your entire solve function twice. And so that's the main thing to be careful of, is that when you're using asserts that you're not like repeatedly calling functions and doing a lot of extra work. Enrique Kai, glad you're enjoying it. Yeah, glad you're learning a lot. And well, we still do have one more problem to go over. NumArt asks, have you ever used any tools to check your solution against the correct brute force? Yeah, definitely have used brute force to check my solutions. Personally, I have like a testing script which just runs the test case generator code and then runs the solution and then compares the outputs. But I mean, there's a lot of ways to do this. Yeah, you can do it yourself. You could probably just write like a Python script, or you could even write a C++ script. If you want to, if this is like a technique you want to use a lot, it's good to just set up a quick script to do this. Okay, looks like we're getting a couple more questions about E before we jump to F. So someone said there's a binary search tag in E. I mean, anyone can add tags, and so someone can just add a tag that's like some weird solution they did. Personally, I wouldn't use binary search for this. I think it's much easier to use the frequency array. I guess you can, if you just sort A, you can do kind of the frequency counting with a 2-pointer sweep. But I think this setup is just a lot easier. And then someone asked, what's the purpose of this type of statement? It's guaranteed that the sum of n for all test cases doesn't exceed 2 times 10 to the 5th. Yeah, so that's a good question. The reason is they want to have a lot of test cases in a single file. So they can have up to 2 times 10 to the 5th test cases. I don't know why they go quite this high. That seems pretty unnecessary to me. It seems like they could go to like 100 or 1,000, that'd be fine. But basically, if they don't give you this guarantee, then you can have 2 times 10 to the 5th test cases where every n is 2 times 10 to the 5th, right? And so then, the sum of all the n is just huge, and like there's no way you can even read all the input in time. And so this is why they do this. They guarantee that basically that the problem is solvable. And so here it's kind of implying that if you write like an n log n algorithm or something like that, then it will be fast enough. Yeah, the VODs are on Twitch. Thanks, Slobe, for putting the link. You can also just do this command and it will, the Streamlabs bot will share that information. And anyone can do that command, so you can also do it, Slobe. Yeah, I may do a Sublime setup stream at some point in the future, not sure yet. And my scripts are not on GitHub, but I'm still working on like figuring out what to put on GitHub. So if I do, I'll make a post. Okay, so we do want to go into F. We have hydrate. So Crow, I think Demoralizer did a graph stream, so make sure you check that out as well. Okay, so For F, we found n segments on the street. It's a funny way to describe it. A segment is described by two integers L and R, which are the beginning and the end. And basically, we believe that a set of segments is good if there is some of the segment, or there's some segment in the set. For some I, we pick it, Li, and it intersects every other segment from the set. And the intersection can be a segment or it can be a point. So for example, this set of segments is good since 2, 3 is our central segment. 2, 3 overlaps with 1, 4. In fact, 1, 4 contains 2, 3. And then 2, 3 also overlaps with 3, 6 at the single point 3. And so we're good. So that's allowed. But this segment, or this set is not good. 1, 2, 2, 3, 3, 5, 4, 5. For one example, 2 and 3, or rather, regardless of which segment we pick, there's nothing that will overlap with everything else. In some sense, like our best chance here is kind of 2, 3, or maybe 3, 5. But the problem is 2, 3 doesn't overlap with 4, 5, and then 3, 5 doesn't overlap with 1, 2. So we want to know what's the minimum number of segments we need to delete so everything else is a good set. And I believe, yeah, the answer can be 0. So I think this sentence is pretty misleading. I would take that out. But anyway, we're trying to figure out the minimum to delete. So ultimately, yeah, we need to figure out like, okay, how do we think about like deleting to get to a good set? Well, first of all, we can always have at least one segment remaining, right? And so when we have that good set, there will be at least one of the segments that can be kind of the key segment Li, Ri. And that segment has to touch everything else, right? And in particular, the only way for two segments not to touch is if one of them is like completely left of the other one. And so the right end of one is less than the left end of the other one. And so, yeah, we can think about this problem a couple different ways, but basically in the end, we need to have one base segment that touches everything. And so for that reason, we can think about looping over the base segment, which one is the base segment, and try to see if this is the base segment, how many things do we have to delete? And so that feels like a much more kind of doable problem. So I'll just make some more segments to illustrate here. Okay. And then as an example, let's say this one is our base segment. Then essentially we can just loop over every other segment. And if the segment has some overlap with our base segment, we can keep it, right? So this one we can keep because it definitely overlaps. This one we can also definitely keep. It definitely overlaps. And then this one overlaps at the 1 point here, so we can keep it. So we can keep basically 3, 4, and 6. But then 2 we'll have to delete because it's too far left. And then 5 we'll have to delete because it's too far right. So we can realize then that there's only 2 cases for segments that we have to delete, assuming we picked our base segment. And that's segments where the R of the segment is less than our L, and also segments where the L of the segment is greater than our R, our right end. And the other key thing is that there's no segment that can do both of those things, right? It's either left of us or it's right of us, but it can't be both. And it can be neither, like this one, but it can't be both. So if we want to calculate all of the bad segments for a base segment, yeah, it's just simply the count of segments with R less than some amount, plus the count of segments, which is this, plus the count of segments with L greater than some amount. And that actually turns out to be quite easy to optimize. So the base solution I'm describing here is n squared. But if we want to do that faster, we can just do this counting faster. And the way that I did it here was basically I read n, I read L and R, and then I made an ordered set of the L's and of the R's. Ordered set is just from this GCC kind of extension called PBDS, which is policy-based data structures. I think there was a good post from Chile, maybe, policy-based. Looks like I'm having or maybe it was Adamant. Yeah, okay, this was the one I was thinking of. And then they also have hash tables. So check those out. Put these links in the chat. And this is kind of the more official documentation here. And so this is what I did. Basically just put everything into the sets, and then you just do two binary searches. It's basically like STL set, except you can count, for example, given a value, how many things in the set are less than this value. And so that's what I do here. I'm just counting R's that are less than Li, and then I'm counting L's that are greater than Ri, which I do by subtracting from n. So that's what I did on this problem. It turns out you don't even need these order sets here, because the reason this would be helpful is if you do things like you insert some, and then you query some, and then you insert some more, and then you query some more. So in this case, we do all the inserting, and then we do all of the querying. So it's just a static array. And so actually, I could actually totally rewrite this. So I'll actually do that now just to illustrate it. So we don't need these sets at all. We could just make sorted lists and then binary search them. So I'll just make two vectors, L's and R's. L's, push back Li. Yeah, and so now basically what we're doing is, so first let's count the R's that are less than Li, and that'll just be lower bound of R's, and then secondly let's count the L's that are greater than Ri, and that will be n minus upper bound because upper bound points to the first thing greater than this, and so upper bound minus begin will give us the number of things less than or equal to it, and that should be, yeah, that should be our solution. Okay, looks good. And I'll actually just submit this too, just to do a quick check. And yeah, so that's accepted. So yeah, what I actually submitted in the contest was something like 4 or 5 times slower, which is fine. But definitely just sorting and using lower bound will be a lot faster here. And yeah, overall pretty simple solution. Definitely, I guess I can even make it a little shorter like this. Yeah, and so that's now we're like at a really quite short solution. And basically, yeah, the main idea was just to figure out, what's our base segment, and then given that base segment, how many things are bad. And the bad things are just things that are too far left, things that are too far right. And we can count that this way. This is just the things that are too far left, and this is the things that are too far right. And I guess I'll just submit it one more time. Just for fun. Yeah, so the memory got better because we're not using pushback anymore. Pushback does this thing where the vector size doubles over time. And so now, because we're just setting it to be equal to L and equal to R, it can use exact sizing instead of the same way we did here, instead of doing this doubling thing. But obviously the runtime is the same. We have a hydrate. Acton says we can use ls.end minus. Yeah, that's true. I never really do that personally, but it's also fine. So upper bound tells us like the first thing that is good, and then from there to the end, and so we can just do end minus upper bound. And yeah, I mean, that's pretty nice. That's pretty clean. So I guess we'll submit one more time. And that way, like, if anyone is in chat and you want to find the code, it'll be in my submissions. Awesome, NumArt. Glad you're enjoying the stream, and glad you're learning a lot. We had a couple questions. Momentum2 asks, how do you make sure that all subsegment intersect? So I think you might want to reread the problem. This is actually something that took me like half a minute to understand properly. So one example is if you have segments like this, if you have 1, 3, and then you have 2, 5, and then you have 4, 6, you actually don't have to delete anything. The reason is you can take 2, 5, 2, 5 intersects 1, 3, and 2, 5 also intersects 4, 6, and you're good. Even though 1, 3, and 4, 6 don't intersect each other. So you don't have to make all subsegments intersect. You only have to make everything intersect one kind of base segment. Lawar Ganaira, I think you're asking B. Yeah, so for B, if you missed the earlier part of the video, here's the link. You can check it out there. And otherwise, maybe someone in chat. It looks like Ivanio CF is responding, so hopefully that helps. Okay, yeah, that's pretty much it for the contest analysis. Were there any questions about things that I said that maybe were unclear or so on? Usually when I ask this, people start asking about, oh, I missed problem C, could you go over that again? I won't go over the same problem again. It'll be in the video if you want to check it out. But yeah, if there are any just kind of more general questions, like for example, something like, oh, how would you approach a problem like this, like D or E or whatever, let me know. Enrique Kai, so I've been doing a lot of post-contest streams lately. And I mean, the streams feature is actually, like this thing, is actually really new. The first one was something like, yeah, end of October this year. So it's only been around for like less than 2 months. So I think it's, I think it's a really good feature. I think people are really enjoying it and learning a lot. So a lot of us are planning to, I know like Eknerwall and I are planning to definitely do more streams, so we'll try to keep it up. Awesome, LM10 Piyush. Glad you're enjoying it. Oh yeah, Devil A. Bonsall asked for, could you explain your templates of modular and factorial in problem E2? Yeah, so that's a good question. I think that's a good thing to cover because it's also a pretty general thing that you can use for a lot of problems. So for me in particular, I use this template. So this is my modent. It basically has all the kind of basic features you would expect. Constructors for different integer types. There are ways to do explicit cast to int and so on. And then just all the basic math operations, plus equals, minus equals. This is like a Codeforces 32-bit thing that makes it faster that isn't super relevant anymore because now I use 64-bit, but it was helpful in the past. Yeah, multiplication, division, so on, even plus plus, minus minus. Basically all the things you would want to like just treat it like a normal number. This is a setup to prepare inverses quickly. This computes the inverse. We have pow and log time, and that's pretty much everything. And then based on this, we have factorials and inverse factorials. So the idea is that factorial n is going to be this, and then inverse factorial n is going to be this. And 1 divided by n factorial is, modulo this thing. So it's the inverse of n factorial. And basically the way we prepare it is like this. So we take in a value that we want to prepare for. This is like a quick trick to basically in a problem, if you call, choose 1, then choose 1 something, choose 2 something, and choose 3 something, and so on, you'll end up calling this prepare function a lot. And so this is kind of a trick to just, it's similar to like how vectors grow and like doubling. They double in length each time. We want to make sure we don't run this function too much. It actually wouldn't be that bad if we ran it too much, but I just figured this is an easy thing to add. We have a hydrate. I can roll says, wait, you compute inverse every time for inverse factorial. Yeah, so the reason I do that is I actually have inverse code up here that computes a whole bunch of inverses in O of 1 per inverse. And it goes up to about 1 million. And this is like a tricky inverse computation. I think there was a thread on CF about it. I don't know if I could find it right now, but basically the inverse of I is equal to the inverse of our modulus. Let's say P mod I times negative P floor division of I. Yeah, it only works for primes. That's true. But the main thing is that if we aren't doing a prime mod, then we won't want to do inverses at all. So we'll just avoid doing inverses. Yeah, so what you can do is you can also compute the inverse of factorial n and then go down. But that runs into the problem I was describing where if you call choose 1, choose 2, choose 3, and so on up to n, you'll get n log n runtime. I guess that would be alleviated by this, which is decent then. But because of the setup I have where I have this inverse precomputation, then this will just be, generally speaking, O of 1. And so that's fine. Yeah, and so the factorial itself is really simple, just multiply by I. Inverse factorial is divided by I. Ideally, yeah, you should make this code O of n instead of O of n log n. The way that Eknerwall was describing is you just compute factorial, then you compute inverse of factorial n, and then you can compute, for example, inverse factorial I is just going to be I plus 1 times inverse factorial of I plus 1. Right, because this is 1 over I plus 1 factorial. if you multiply that by I plus 1, you'll get 1 over I factorial. And that way we only have to compute one inverse, and then we'll be good. Yeah, inverse mod nod prime is well defined. It's just sometimes invalid. Yeah. So in general, I think we don't want to, like if we get a problem where we're modding by non-prime, we generally just don't want to do inverses. I have a version that I am keeping around that does what you're describing. It just does extended Euclidean algorithm. But for the most part, I use this version now, which does these fast inverses. And that was actually a recent thing that I set up. The main reason that I set this up with this array, I compute up to 1 million. The main reason I set this up is I just had enough times where, for example, I was doing a problem where it was like an n squared dp, and n was up to 5,000. We have a hydrate. N was up to like 5,000. I did an n squared dp, and then I just got TLE. And the reason I got TLE is because I actually used division in my dp, and like it would be really easy to. I was actually dividing by the same number every time. I was dividing by the same number every time, and then it would be super easy to just like save that one inverse and just use multiplication. But my code, like it doesn't know to do that, obviously. So my runtime was actually n squared log n, and I just got TLE. Yeah, and I just got fed up with that, and so I set up this method to save like the first 1 million inverses, and then for other inverses you can actually. What's kind of cool is it's instead of being like log 1e9 time, it's only log 1e3 time, because if you have a number that's like about 1 billion, you just have to do this algorithm until you go below 1 million. Yeah, and I just picked this number 1 million because it's like, it's not too big, it doesn't take too much memory, it's about 4 megabytes, right? And then also I've like timed this code, it takes like 20 milliseconds at most, so it's super fast, and it's not a concern for using up a ton of time. GM Mark Zuckerberg asked, did I quit AOC? No, I didn't really quit it. I just never really, like I was never really super consistent about it. I honestly was just like doing other stuff the past couple days and just forgot about it. And then I was like, oh, it's already like 11:15, whoops. And it wasn't that big of a deal. I think this happened to Eknerwala once, and so unfortunately he dropped a bunch in the rankings, but I think he's still top 3 now, so pretty impressive. Oh, Ivanio CF said, I accidentally calculated the first 2 times 10 to the 5th factorials for each test case. Yeah, so that's why my code is set up where it kind of has a static variable that saves, oh, how far have we already prepared up to? And then that way we never do any like redundant computations. Oh, did Beta Veros pass Nick? Oh wow, 3 points. That's pretty crazy. Yeah, I think where was that standings page? Yeah, clist.by has some really nice standings. So yeah, so he missed this day, but he's still actually 3 points ahead. And then Andrew missed this day. And then, oh, here's me. Yeah, I just missed a bunch of days. But anyway, it's fine. Yeah, I actually see a ton of people that I recognize up here, which is pretty cool. Yeah, I think around the like 40-ish range, you get to a lot of people where they don't really do all of them. And yeah, I don't really see anyone in this range who did everything, so I guess it kind of makes sense. Or well, I guess it's hard to say, because if you weren't the top 100 then you would still just show up as a dot even though you did it. I found a CF. I solved all days and I still have 0 points. Yeah, I guess it's really like, it's really predicated on you like being fast. So yeah, I guess, you know, for these guys, it's clear like, oh, they actually missed a day rather than they just didn't get any points. But yeah, they could do something where, you know, it's like a smoother curve where anyone who solves something gets some points. I think that would be better. This is too much like enforcing, oh, you have to be top 100 to get anything. Okay. But yeah, all right. I am gonna start wrapping up now. I think someone said, let me see. Did someone say Ericto's still streaming? Okay, yeah, I see him here. So, okay, yeah, I guess we'll just go ahead and raid Ericto. Cool, thanks everyone for coming. Saw a lot of people saying, you know, they're learning a lot from the stream, so glad you guys are enjoying it. And cool, see everyone next time. And let me just set up the raid. I Watch Coding says, what is raid? So raid is a Twitch feature where when one stream ends, we have a hydrate random coder. Leibniz Disciple, I just started watching. If you want to check out the other problems from today, you can check this link. But yeah, raid is something on Twitch where basically after you finish one stream, you can go directly to another stream that is usually a similar topic where that way you can just keep like a more continuous stream setup. And I think it's a really good feature for Twitch where streamers can kind of like help each other and promote each other and so on. So yeah, thanks everyone. We'll see you next time.